first one will be given by Professor Steven Louie from University of California, Berkeley. So we're setting up the computer right now, and we're very honored to have Professor Louie with us today because he just won this Materials Theory Awards from MRS 2 weeks ago, right? So so today he's going to tell us about novel interaction and correlation phenomenon in atomically thin quasi-2D materials. We're going to have some challenge here, right, to show. Okay, so let us welcome our speaker.
Okay, well, can you hear me? Thank you very much, Mayan, for the kind introduction. And I'd like to also thank all other organizers for the opportunity to give this talk today. I'm delighted to be here at the NCTS again because I have been involved with the center for many years, since its inception actually. And I'm really glad that you guys are having this series of meetings every year now on condensed matter theory and also in theoretical physics. So what I'd like to do today is to tell you a bit and discuss with you some of the recent work that we have done on looking at some of the properties of atomically thin quasi-two-dimensional materials. And before I begin, let me just acknowledge that the work is supported by the Department of Energy and the National Science Foundation of the US. Okay, so there have been a lot of interest nowadays on atomically thin, we call quasi-two-dimensional systems. One of the most famous example is graphene. Graphene is just a single layer of graphite. And of course, there are many other layer materials in nature. And in fact, one could make this kind of atomically thin 2D crystals from those materials. For example, you have this class of transition metal dicarbogenized. Some of them are semiconductors, and some are metals, and even superconductors at the monolayer level. And you have insulators, and even system that becomes a very good superconductor when you get it down to a monolayer form sitting on top of a substrate, and many other examples. So what I'm going to do today is mainly focus on non-graphene systems, the transition metal dicarbogenized systems, some of the other monolayer or few layer crystals. And of course, because you have many of this kind of 2D crystals now available, and they are of different properties, and people are actually making or thinking about stacking them or making heterostructure using them to get out perhaps even more novel properties. So before I begin, let me just emphasize one aspect of 2D materials, this kind of quasi-two-dimensional atomically thin materials. There are two features one should remember when we discuss the properties of this kind of system. First, of course, you're in reduced dimension, so you have enhanced Coulomb interaction in such a system. Another feature is that, this one is less well known, is that you could have very strange and strong spatial screening in such a kind of system. For example, if I have a 2D material right here, and if I have two charged particles, in such a system, what you would find is that the interaction of the two particles, charged particle, differ quite a bit from the Coulomb interaction. If you look at the dielectric screening function of between such two particles, you will find, as usual, when the two particles are very close to each other, there's no screening, so it's 1. When the two particles are very far away from each other, in fact, you see that the field lines go outside of the system because you are in a three-dimensional world, and therefore screening is also not effective. It becomes 1 again. So that means you have this very strange behavior with a dielectric function. When you're looking at a function of distance, it goes from 1 to some maximum value and back to 1 again. Another thing is that you put such a material on top of a substrate, then you see that the field lines penetrate in the substrate, and the substrate start affecting the interaction between the two particles. So substrate and environmental screening are very important in affecting the property of the crystals. So when somebody tells you the property of a particular 2D material, one should really know exactly in what environment the material is in. So I would show you some example of that later. So basically this is going to be the outline of my talk. I will begin by looking at some of the interesting phenomena in transition metal dicarbogenide monolayer and field layers systems. In particular, we're going to look at the influence of many-body effects on the photophysics of this material. We find that there is a diversity of strongly bound exciton in this class of material. Another very interesting phenomenon we find recently is that we find that massless excitons exist in this material. It has a very interesting new quantum number associated with those states. We call those Orfali pseudospin in the system. And also the plasmons in this kind of 2D crystal can be very interesting, and in fact it can be tuned by using substrate and screening effect. That could be very useful in plasmonics. And then toward the end of the lecture, we're going to look at some other interesting phenomena in other quasi-2D systems. For example, if you look at the monolayer of gallium selenide, you'll find that you could make it to be a magnet, and the magnetism in this system can be tuned by gating and doping the system, and the system becomes a half metal. One finds also a very interesting switchable transport property in black phosphorus. And finally, I'm going to mention something about graphene. What we find is a really surprising result. That is, we find that the electrons can be made supercollimated, propagating in such a system when you apply a 1D disorder potential to it. So basically, we're going to look at the electronic properties of the 2D materials, in particular how many body interactions in such systems could modify the properties from an initial point of view. So the central quantity that's of important to the discussion is the self-energy of the electron due to many body interaction. Such self-energy will modify the energy dispersion of the quasi-particle, give rise to a new effective mass in lifetime when you compare to a mean field or non-impacting particle. So you look at the spectral function, then you see that, as we all know, both the imaginary and the real part of the self-energy comes in. And of course, the self-energy has many contributions due to the various interactions in the material. electron-electron interaction, electron-phonon interaction, and so on. In this talk, I will mostly focus on electron-electron interaction and then touch a bit on electron-phonon interaction. So what we want to do is to study these properties from first principles, and we use a interacting Green's function approach. So for example, if I want to look at the quasi-particle properties of such a system, we use a particular many-body perturbation approach, which is called a GW approach. That is an approach to expand the self-energy in terms of a series of diagrams. Instead of using the Coulomb interaction, one uses a screen Coulomb interaction. And by taking the first term, this is called the GW approximation. The key here, of course, is that you're looking at the screen Coulomb interaction. Therefore, it's much weaker, and one expected a more rapid convergence. And then to look at the optical properties, one has to include the interaction of the electron and hole, the so-called excitonic effects. And one has to look at the two-particle Green's function, the interacting two-particle Green's function, and solve the so-called beta-salpeter equation. It turns out that the electron-hole interaction, we call it K here, can be obtained once you know what the self-energy is. So within the GW approximation, you could actually derive completely, ab initioally, the electron-hole interaction. And this interaction has two terms. One is an exchange term, which involves the big Coulomb interaction. And then one is the usual attractive direct term involving the screen Coulomb interaction. So within this approach, then you could get out a whole host of physical properties without any empirical input. For example, the quasi-particle dispersion and lifetime, optical absorption spectra, the exciton binding energy, wave functions, lifetimes, and so on. So let's turn to the first topic I would like to discuss, which is the photophysics of the monolayer and two-layer transition metal dihydrogenase. There are many different experimental ways now to synthesize this kind of system, and this is a very rapidly exciting field in condensed matter physics nowadays. So here I will first focus on monolayer molybdenum disulfide. Molybdenum disulfide in the bulk is a layer material which consists of weakly interacting layers. Each layer is formed by a sheet of molybdenum atom sandwiched between two sheets of sulfur atoms. Looking top down on one of this layer, you have a structure like this, which looks like graphene, a honeycomb structure. And this is a side view of one of these layers. If you look at the optical gap of this material, in the bulk, it is actually indirect gap material with a gap around 1.3 electron volts. In the monolayer form, it becomes a direct gap with a value around 1.9 eV at room temperature. Unlike graphene, however, this system is a semiconductor. It has no inversion symmetry, and it has a very strong spin-orbit coupling in the system. Because of this very strong spin-orbit interaction, the low energy excitation states, which are located at the two corner valleys in the Brillouin zone, become inequivalent. They actually have very different spin textures. You could selectively excite one of these valleys by circular depolarized light. So now for this system, you have this exciting possibility of controlling the charge, spin, and Wally degree of freedom separately. And this lead to very interesting possibility for develop what we call photoelectronics. And also, as you see later, there are very interesting exotonic physics in this system. And some application has been demonstrated for this material. So let's first look at the photophysics of a monolayer. So here is the calculated band structure of moly disulfide monolayer. The blue lines are the LDFT, LDA bands, and the red lines are the GW quasi-particle bands. You see that there are significant modification. The self-energy correction to the band gap is around 0.7 electron volt. And you see even for the occupied valence bands, there are significant changes due to the self-energy effect. The quasi-particle gap is 2.7 eV, at least according to the calculation. As I mentioned before, the measured optical gap is around 2 eV, so that means there's a huge exciton binding energy in this system. So here is the calculated absorption spectra for moly disulfide monolayer, and we will compute the experiment later. So plotted here is the absorbance as a function of photon energy. If I neglect electron-hole interaction, then I get this red curve here. Basically, it's calculated with the interband transition model. Now, when you turn on electron-hole interaction, then you have this green curve. It's completely different. You have many, many sharp peaks now. And the reason you have all these sharp peaks are these are strongly bound exciton states. You look at the band structure, you see that there are interband transitions in the very part of the Brillouin zone. The direct gap is at K, so here is a spin orbit split top of the valence band. You have an A transition, B transition, and a C transition. And each set of transitions actually give rise to a series of strongly bound excitons labeled A prime, AW prime, double prime, and so on. So the exciton binding energies is in the order of 0.7 electron volt, much bigger than bulk semiconductors of the same size gap. Another important thing to note is the absorbance. This is the absolute absorbance for a monolayer is huge. It's in the order of 20 to 40%. So that means light coming in will be absorbed by 30 to 40%, even for a monolayer of such material. And this arises because you have very, very strong excitonic states. It drops all the oscillator strength from the high frequency transitions. How does it compare to experiment? This is the comparison between the results from Tony Hines' group. You clearly see these two peaks here correspond to the first two peaks, and then there's a broad absorption background at higher frequency. Now, it turns out that this broad absorption really does correspond to the excitonic state here, except that in our calculation, we have neglected one effect, which is the electron-phonon interaction. That also gives rise to a self-energy to the electronic states. When we include the electron-phonon self-energy, then you get this green curve here. And now you have really nice agreement between theory and experiment. And even this C peak that was predicted in the theory has been recently found in resonance Raman scattering experiments. Now let's look at the excitonic levels more carefully. There are many, many excitonic levels. Then let's just focus on the A series. And there are both dark and bright states. Dark means optically inactive in linear optical experiments. And what you see is not only the lowest energy state is strongly, has very large binding energy, all the excited state also has strong binding energies. And you could think of an excitonic state as just a linear combination of free electron hole pairs. And this coefficient, in fact, is the solution of the beta-salpeter equation that we solved. So by plotting out this set of coefficient in k-space, you have a k-space representation of the wave function of the exciton. So here's for the lowest energy state, this is for the 2p, 2s, and so on. So one thing you should know is that the wave function in k-space is very, very much focused or localized in a very small region to less than 3% of k-space. So that means in real space it's very extended. The excitons actually has a radius of an order of few nanometer or more in real space. So even though this exciton has a binding energy about 1 electron volt, it's still a linear exciton in the sense that the wave function is very extended. Now, how's that compared to a 2D hydrogenic like model? Suppose I take the band structure of mono disulfide and then calculate within that hydrogenic model of what the excitonic state would be like, and then put in one parameter, the dielectric constant, so that I adjust the lowest level to be the same as that initial calculation. And what you find is this series of states. So you see that there are two major differences. One is that the high energy has a very small binding energy. A high energy state has a very small binding energy in the hydrogenic model. And secondly, we see that the ordering the levels are different. In fact, in the initial calculation, the 2p level is below the 2s, and 3d is below 3p, 3s. This, in fact, is related to this strange and spatial dependent screening that I mentioned in the beginning. Suppose I map our calculated three-dimensional dielectric matrix into a 2D problem and solve a hydrogenic model like this. What you will see is that in a regular hydrogenic model where you just use one dielectric constant, a corresponding setting epsilon to be a constant. So this would be the hydrogenic model. In 3 dimension, of course, this is a good approximation. The dielectric screening becomes a constant, rapidly approaching constant at a few bond lengths away from the hole or the electron. However, in 2 dimension, what we find from our calculation, in fact, the dielectric function has very strong spatial dependent. It's 1 at 0 distance and 1 at large distance, as I explained earlier. And so, if you look at the 1s state, then it's the electron and hole at a distance that is very close to this screening peak, and it has certain interaction strength. But if you look at a 2s level, then the electron-hole separation is mostly in the unscreened regime. The electron-hole interaction effectively becomes much stronger than that of the lowest energy level. And that's why you have a much stronger binding energy for the higher excited states, exciton state. And similarly, you could understand why the 2p level actually is lower than the 2s level. So, because of this a large number of very strongly bind excitons, it gives rise to a lot of opportunity for studying interesting exciton physics in 2D systems. And in fact, there are many experiments have been done to probe those excitonic states. Another very interesting system is that if you put 2 such layers together, 2 different type of layers, in fact, what you could what you can show is that you could form spatially indirect excitons. That is, the hole would stay in one layer, and then the electron would stay in another layer. And those kind of excitons, in fact, still have very strong binding energy in the order of 0.4 electron volt. So now you could really study a number of interesting physical phenomena at room temperature because the strong binding energy, such as exciton condensation, Coulomb drag effects, and so on. In fact, this predicted dark excitons and the reverse quantum level ordering has been seen experimentally by my colleague Shang Zheng at Berkeley. What they did is to probe the dark excitons to do a 2-photon luminescence experiment, exciting the system with 2 photons into a dark state, and then look at how the light comes out. And what they find indeed is that the 2p is lower than the 2s state, and the dark levels are in fact in very good agreement with ab initio calculation. Now let me turn to the screening effect, or substrate effect on the 2D materials. So here, screening is highly non-local, and it depends on precision R, R prime, and frequency. We now have a way of actually calculating those kind of effects due to a substrate. So let me illustrate the importance of substrate screening with this simple example. Suppose I have a monolayer molybdenum on top of a bilayer graphene, which is somewhat metallic. Then if I have a negative point charge here, then the substrate, in fact, try to screen this charge, and there will be additional induced screen charge, and that's what's plotted here. So you see that there's a piling up of positive charge to try to screen this point charge, but there's actually an over-screening region here. So this whole thing is highly non-local. It's very difficult to try to model that with any model dielectric effects. So to illustrate this, we look at monolayers, molybdenum on bilayer graphene. First, this is the calculated result with no substrate. So the experimental situation would look something like that. In fact, that's been done by my colleagues at Berkeley. So there's no substrate here. You have a certain quasi-particle gap, optical excitation, and the lowest energy exciton, binding energy. If you put the same monolayer